Yeah, this has come a long way. I started teaching at AR in year 2000, and I remember in year 2000, I was carrying one of those MP3 players, kind of like a standalone MP3 player that runs on a double A battery. Okay, you guys may remember your parents, having one of those things, right? But some of those also has a mic and they can record. So at the time, I was wearing mostly polo shirts with a pocket or something that has a pocket. So I would just kind of put that thing in a pocket, and so I would be uploading my audio only, recording of classes, to my own website, and it will be encoded in SPX or Speaks, as a format, because that was the highest compression ratio available at the time. And we didn't have gigabytes of storage, on any type of server for a reasonable amount of money. So it took a long time until like 2000, maybe 10 or so. Then I started to use YouTube to stream videos. So that's a and at the time in 2010, YouTube did not allow like an upload of something that's an hour and 20 minutes like our classes. So I had to record the whole thing onto a single file, go home, and then run a script to chop it into 15-minute segments, upload the individual segments, and then stitch the entire thing back into a playlist. So that when students play the playlist, it will automatically play the next clip, and then the next clip, and then the next clip. So this definitely had come a long way, before we get to what we can do now. And yet, how many people do it on this campus? I don't know. I really have no idea. Two? Oh, Iraj does it too? Yeah, Iraj actually talked to me about this, and I think he felt that it was actually useful, to him and his students. So that's why he is doing it. All right, cool. So a few things, okay, because I got a request from one of you to talk about Turing's machines, especially automata. So the term is automata, AUTO, auto, and then mata. And automata refers to, okay, there are several definitions. But one definition of automata is based on Alan Turing's theories. So if you look up Turing, then you'll find a lot of references to that. I'm not going to get too deep into Turing machines and how it came along, but all this theory had a background of deciphering encrypted messages back at the end of World War II, and it had to do with the recognition of a particular message at the beginning of the messages. So so if you trace back to that history of all of these theories, it actually starts to make sense, okay? Because it's all based on, what is the incoming symbol, what is the outgoing symbol, where's the stop state here, which basically says yes, we have recognized that particular string, and so on. But basically, everything that we do today with modern computers can be theorized using these particular theories. And beyond, okay? Because our current machines are not even as powerful as the theoretical Turing machines. Because those things are supposed to have an infinite number, or it's supposed to have a tape that has an infinite length. And we don't have any computers that had infinite storage of any kind. So very interesting stuff. So we might get to talk about this later on in this class, after we get graph theory, not graph theory, but search algorithms out of the way. So just a little bit of context for that discussion. And we are going to continue with the trace. Remember last time we were kind of halfway done with the trace, and I said, with the way that I trace the algorithm, it is actually easy to resume. So that's what we'll do today. All right, so a few things to set up here. And let me get the tablet screen started first. And then we go to 440, 418. And there we go. So we got the graph. And now we just need to start up the spreadsheet. And it should be here somewhere. I think that's October 31st. pretty sure about that. There we go. All right, so now we can resume our trace. So at this point, what we already know is we have replaced, so if you look at this change here from row 8 to row 9, that kind of tells you where we are at with the algorithm. So if you compare row 8 and row 9, we can see that W is A. We are considering the incoming edge of AC, okay, which is here. And that help us discover a shorter path in order for A to go to our destination, which is E. So that's why we updated L of A to 3.1, which is the length of the shortest path known at this point from vertex A to A destination state. We only got one destination in this case. It's vertex E. And as a result, we have to update another thing as well, because before it was going to vertex D to get to A destination. Now that we have discovered a shorter path by going to vertex C, we erase AD as an edge from E prime, and then we add a new edge of AC into E prime, because that old edge was not on the shortest path anymore. So we have to remove it and replace it with an edge that is actually on the shortest path. So are we good so far with this? Okay. I should have replayed, like, the last 3 minutes of the previous lecture and then just put a big sign saying previously on cisp440. But that's kind of where we were, okay? So now we have to look into vertex C and go like, do we have any other incoming edges? We have one more that's coming from B. So let me get this one out of the way. So let me right click, go to panel preferences. So right now I have it to be hidden intelligently, which means if something is over it, it should hide. So I would just go ahead and make it so that it's always hiding. There we go. So until I actually go to the bottom, it's just out of the way. So that gives me a little bit more screen area. All right, so now we go back to here, and we go like, well, there's another incoming edge from B. So we'll have to consider BC now. So we look at BC and go like, is this edge giving me a shorter path from B to a destination? Well, let's find out, okay? So if B is to go through C to get to destination E, what would that length be? What would the length of that path? It will be 4, because C, the length of the shortest path from C to a destination is known to be 3 already. And then the incoming edge from B has a cost of 1. So 1 plus 3 is 4. So now you have to look at that 4 and ask, is that shorter than the currently known, the length of the currently known shortest path from vertex B to a destination? So you look up L of B at this point, which is infinity. Well, 4 is less than infinity. So now we have to go through the update process. Is that making any sense? So we just discovered that, and the first thing we do is to update L of B. So now it's 4, so that we remember the length of the shortest known path from vertex B to a destination is 4 units. And then we have to make sure that we remember that particular edge. So we have to, okay, so I'll just retype the whole thing. So we now have DE, AD is fine. Oh, okay, we just erased AD before. CD is fine, AC is fine, and now we have BC as well as an edge in E prime. And there's one more thing we have to do. We have to also add vertex B into the set Q. So now the set Q has A and B as its elements. The purpose of Q is to keep track of vertices where its own length of shortest path has been updated, has just been updated. Because that update can potentially affect things that are upstream, and that's why we have to revisit those particular vertices and go like, well, the last update of this vertex may update and find a shorter path of incoming edges to those vertices. So that's why we have to kind of keep track of a set Q in order to to serve that purpose. So are we good so far? Yes? Okay. So now we're done with the inner loop, which is basically just looking at all the incoming edges into vertex C. So that part is done. We get back out to the outer loop. The outer loop is looking at set Q and say, is it empty? Nope, it's not empty. If it's not empty, then we have to find the most, quote unquote, most promising vertex, which basically is just the one that has the shortest length, the length of the shortest path is the least. Okay, so out of vertex A, which currently has a length of shortest path of 3.1, and vertex B, which currently has a length of the shortest path being 4, the more promising one is A. So we choose A to explore first. So in the outer loop, in the while loop, this time we choose A to be vertex V as a variable. And then we look at all the incoming edges to vertex A. Well, we got one going into vertex A, which is from vertex B. And now we look into, I'm just separating the screen so that I can scroll the bottom without affecting the top. All right, so the incoming edge to vertex A is BA, which is this edge over here. So now the question is, am I discovering a shorter path from B to a destination? Well, let's try to find out. How much does it cost from A to a destination? Well, according to this, it's 3.1 units. How much does it cost to go from B to A? 0.5. 0.5 plus 3.1 is 3.6. So I know that I can have one path that has a length of 3.6 units from B to a destination state of vertex. What is it currently? Well, according to this, currently it has a length of 4. Guess what? We just found a shorter path. So now we have to go through that update process again. So that update process has 2 things to do. Well, in this case, almost 3 things to do. The first one is to update L of B so that it is now 3.6, because 3.6 is the actual length of the shortest known path from vertex B to a destination. The second thing we need to do is to update the Eeprom set, because now we have to copy and paste what we had. Look at the BC, which is the edge that is now going to be replaced. So I'm going to add the new one first, and then I'll erase the other one. So we'll go from B to A. Okay, using the wrong paren here. There you go. And then the other one now has to be erased because that one is no longer an edge on the shortest path. So we have to get rid of that one. And I don't want to just get rid of it. So strike through clearly indicates that we are deleting that particular edge from the set. And over here, oops, I forgot one thing. I forgot to remove A from the set when we chose A to explore. Okay, so now we're supposed to put B into the set Q, but that's okay, it's already in it. When you add an element that is already in the set, it doesn't really do a single thing because you cannot have duplicate elements in a set. So are we okay so far on row 12 of the trace? That's good, okay. So on row 13, okay, we're getting back out to the outer loop because there's only one incoming edge from B to A. So now we go back to the outer loop. We ask, is the set Q empty? Nope, it has got one element in it. That makes it easy to choose which one we want to explore next. So we choose B as the new vertex to explore. So that becomes the V, or the value of variable V in the algorithm. So that is B. And then we ask, do we have any incoming edges into vertex B? The answer is nope, don't have anything. So there's nothing to do in the inner for each loop because we do not have any incoming edges to vertex B. Then we get back out to the outer loop, which once more asks the question, is the set Q empty? Yep, it is empty now. So now we are all done. So now the question is, when the algorithm is all done, what do we actually end up with? We end up with the L values, okay, which are basically the lengths of the shortest paths from each vertex to a destination, okay? But that is relatively useless, okay? Well, it is useful, but it's not the actual solution. The actual solution is E prime, okay? So what we'll do now is we'll annotate based on E prime. um, in the graph itself. So I'm going to use a different color, let's say green, to only include edges that are in E prime. So we got DE, okay? That's not really surprising because that's the only way to get to E, okay? We got CD, okay? So CD is this edge here. We got AC, and then we got BA. So when you look at the green portion of the graph, that is what E prime is representing. So now the question is, well, what is that representing? The shortest path, exactly. So it doesn't matter which vertex you're on, you just follow the green path, and that will basically guide you to the shortest path to a destination. Is that okay? Now in this particular case, it's really kind of strange because of the way I set up the weight, because now it is just linear, because it's from B, and then A, and then C, and then D, and then E. So it's a very degenerated tree, but nonetheless, it is a tree. What is the property of a tree? There's a root, okay, but the root doesn't make a tree. A root is basically, it's kind of more or less an artificial concept, because if you look at a tree that does not have directional edges, you can actually pick up any node. Doesn't have to be a leaf. You can pick up any node and hang it with that node, and it becomes a tree rooted at the node that you're hanging on to. So, so having a root doesn't make a tree a tree. What else? What else makes a tree a tree? Related to that concept, you cannot go back. Yep.
So you're going less to the right and more left?
Okay, so first of all, there's only one path between any two vertices. Up to one path, okay? So two vertices may not be connected at all, but if they are connected, there's only one path between those two vertices. Okay? That really is what makes a tree, is there's only one path, up to one path between any two vertices. And when you look at E prime, now this particular example is so degenerated that it is not even, it doesn't even look like a tree, even though it is a tree. So in nature, what this tree is going to look like is a main trunk going to one smaller branch going to one even smaller branch, but the entire tree is like a mast. That's what this tree is going to look like, with a single leaf at the very end. But it still fits the description or the definition of a tree, where there's only one path between any two nodes, between any two vertices. Okay, and that turns out to be a very common property, the common property of all the solution graphs. So it doesn't matter what your graph originally looks like, the solution graph of Dijkstra's algorithm will always give you not a single tree, but it will always be a forest. In other words, it can be multiple trees. Is that okay so far? So let me ask you a different question related to what a tree is. What is the nice thing about a tree? Why do you think tree is so studied in computer science? In cisp440, for instance. What makes a tree so unique, so useful in computer science? What do we use it for? Search. Go ahead. It is not. It can be linear, okay. So until you get to self-balancing trees, to make sure that you have all the branches evening out, a tree can be not so balanced. But yes, most of the time we want it to be balanced. Go ahead.
Conceptually, a binary search, which is about the fastest.
So a binary search tree is a tree where, if you construct it in the ideal situation, once again, the depth of a tree is the log of the number of items you want to store. So that means, when you're searching, the search time is also going to be the log of the number of things that you have stored, which makes it really fast. Go ahead.
In a tree, the data is sorted already?
It can be, okay, so depending on what kind of tree we are talking about, like a binary search tree, if you traverse it in a particular way, then you come up with the sorted order of the items that you have stored. But the really nice part about the tree is the minimal graph that keeps things connected. It cannot get any simpler and still retain the connectivity between the nodes. If you remove one single edge from a tree, something gets disconnected. It has no redundancy, which means it is nice from the perspective of being optimal, but it is not so good from the perspective of critical paths, because every single edge becomes a part of a critical path, which is not good if you're networking, right? Because if you're dealing with networking, you only got one path between any two routers. So that means if any connection between any two routers goes down, someone is going to lose connection, which is not what you want. So I just want to kind of point out, properties of a tree, why it is useful, but also why sometimes we do not want a tree. So in the case of routing, we do not want network routing to look like a tree, because that has no redundancy whatsoever. Okay, so are we good so far with what Dijkstra's algorithm do? Yep.
I just had one random question. So, how would you go about proving that this algorithm does indeed find the shortest path?
Now that's a very good question. Okay, which was actually one of the questions in earlier exams. So let me repeat the question. Correct me if I got it wrong. So how do we prove that the Dijkstra's algorithm actually finds the shortest path of all the vertices to a destination vertex? Would that be correct? Okay. So the best way to prove it is to make it proof by contradiction. And you basically say Dijkstra's algorithm did not actually find the shortest path from a vertex to a destination vertex. Okay? So what you then will have to say is to say that, okay, so this is the picture. So let's say we're concerned about vertex V, and here's another vertex. I'll call it X here. Okay, and this is the path discovered by Dijkstra's algorithm. And then here is an alternate path that is actually shorter. So if Dijkstra's algorithm did not find the optimal path, that means this condition has to exist. Now the alternate path may merge with the other path, also. Okay, so you can basically say there are two paths and they may, share certain segments or not, or whatnot. So now the question is, how do you prove this? The dotted line cannot exist by the very virtue of Dijkstra's algorithm. So how would you do that? Now, how is this path constructed in the first place? In other words, how do we add edges onto E prime as a set? There's only one place in the algorithm that can do it, right? So let's go to the nodes first, okay, so I can show you which part we are talking about. And by the way, I'm kind of winging the proof as we speak. Fair warning. But in a way, it's good too, because it kind of shows, it will show at least one of two things. One, I don't know what I'm talking about, or two, how I think, right? So either way, it's going to be useful. All right, so this is Dijkstra's algorithm, and we're going to focus on this part here, and also the previous one. So in order to add an edge into E prime, we have to get to this part. But this part is guarded by this condition. Is that okay? So what condition is it guarded by? It's guarded by the condition of we have to be discovering a shorter path in order to do this. Is that okay? So now what we need to do, okay, using proof by contradiction, is basically to say this is the only way to add an edge into E prime as a solution graph. And it is not possible for this to complete that path that is non-optimal all the way from the vertex V to X. Okay? So switching back to the tablet. Okay, I'm just thinking about how to approach this. So if you look at this, every single vertex along this way, every single edge is added by that piece of code, that single line of code. Is that okay? And we are claiming that there's an alternate path that is shorter. Okay? Now, if the alternate path is shorter, and you can kind of look into one specific case. So we was looking into the specific case where this part is missing, but the other part is already there. Okay? And we are basically saying that if we just complete this part here, that would have been a shorter path. Is that okay? So now the question is, why did I choose this edge to connect V instead of this edge to connect V? It is possible that this one looks more promising. Okay? If this one looks more promising, we would have chosen this edge and added onto E prime. So now the question is, would this be guaranteed on Q and it would just be explored next? It would be explored later on. Because if this is always going to be in Q, that will be explored again, then we would have updated V because of the exploration of this one in Q. So now we have to go back and say, okay, but how can we prove that this is not it is not possible for this one not to be in Q when this happens? And I'm not 100% sure how to do it. But I still think the best way to do it is to prove by contradiction. You basically assume that we found a path that is not the shortest, and then, okay, I think I remember now. There's a corollary to that whole thing to prove it. I'm trying to remember what it was. If we finish the path, I know why. Okay, because Q is added, right? Q has to be added to Q, not Q. Okay, we have to give these vertices names. So we'll name this one W, okay? So in order for W to be connected, having its own path to a destination, means that W has to be at least once in Q. Does it make sense? Because we always add the tail of each edge to the set Q. And W is the tail of this particular edge. So W has to be in Q at one point or another. Does that make any sense? So that means before the algorithm terminates, okay, W can be the very, very last vertex that we explore out of Q, but it has to be explored. So let's say we pick W up from Q, and then what do we do in the algorithm when we have picked up W from Q? We explore all the incoming edges of that vertex, right? And guess how W relates to V? V is one of the incoming vertices of W. So V would have been explored in the for each loop. Is that okay? If V is explored in the for each loop, that means we would have a chance to fix it by erasing this edge, which is non-optimal or on a non-optimal path, and redirect it back to W. But that only proves the case when it is the last one. So you basically now have to work your way back up until you prove that there's no non-optimal path that can exist. Because if a non-optimal path exists, at some point that path has to deviate from a common path onto the from the from the non-optimal path back to the optimal path. And right at that switch, we can use the exploration of this node and go like, well, if at this point it should have connected it here and not to follow this particular path. Is that okay? I know it sounds really vague, but those are the components that we're looking at. And then the reasoning has to do with, if it is non-optimal, then this has to happen. If that has to happen, then we must have encountered that particular line, and that's so you have to relate everything back to the algorithm itself. And it's usually the conditions of the conditional statements that are the most useful, because that is how we steer what is added to the solution graph and what is not added to the solution graph. So I'll clean it up and make a better presentation next time, but it's basically the same idea of, if there was a shorter path, we would have done it already. We would have made that connection. It is not possible to have missed that connection. Is that okay? Any other questions regarding Dijkstra's algorithm? Yep.
Yeah, we say Dijkstra's algorithm, the more rows we have, the less efficient it is.
The more rows we have, routes.
For example, we just had comparison between two. So basically, the higher one, we had to go almost to the end to find the shortest path to the.
Okay, that's
What if you have like 3, 4, 5?
That's a good observation. So you're basically asking a question about the time complexity of Dijkstra's algorithm. In other words, if we make the graph more and more and more complex, how does that change the execution time of Dijkstra's algorithm? So what do you think? So let's go back to the picture of a graph. Okay. Okay, here's a picture of a graph. And you can, in the worst case, you can have a completely connected graph where every vertex is connected to every other vertex, which means you end up with the number is proportional to the square, but it's not exactly the square. Okay, because you want to assume that a vertex does not connect back to itself, so those edges are typically not considered. But it's going to be proportional to the square. So now the question is, does the execution time of Dijkstra's algorithm, does it relate to the number of edges, or does it relate to the number of vertices? Because we have seen how it can re-explore the same vertex multiple times, so we know it's not correlating directly with the number of vertices. So now we ask the other question, is it correlated with the number of edges? In other words, if I have so many edges, does the algorithm re-explore the same edge twice? Does it?
No.
It does not. Okay, very good. Now, why do we know it does not explore the same edge twice?
Store the information, the shortest path from forever.
Because it gets shorter and shorter, right? So because of the value of L, it's getting smaller and smaller. So that means, even though we can explore more edges, but if the new edges are not giving us a shorter path, it doesn't cause the vertex to reappear in Q, and as a result, it doesn't cause any more exploration. Okay, so it does not explore the same edge twice, which means the worst case is just the number of edges. So that determines the complexity of Dijkstra's algorithm.
So it's basically an O n, right?
N squared. If n is the number of vertices, then it's n squared. So it's big O of n squared. Is that answering your question? Okay, very good. All right. So getting back to the notes. Are we ready for A star, the A star algorithm? Maybe? Okay, so the A star algorithm is a little bit different compared to Dijkstra's algorithm. Dijkstra's algorithm is not guided. In other words, okay, let me point out exactly where I mean by it is not guided. When we select which vertex out of Q to pick up on this line to explore, it is really just saying who looks the most promising. And that's it, okay? And quote unquote promising only has to do with the length of the shortest path from that vertex to the destination. That's, that makes it it's non-guided. It is what we call a breadth first search algorithm. It expands, but it expands in all directions. When it's done, it finds the shortest path from every vertex to a destination vertex. And that's kind of partially why it cannot be guided, because it's looking at things from the perspective of every single vertex to a particular destination, so it cannot be guided. The A star algorithm, on the other hand, is guided. So this makes the biggest difference between the two algorithms. When we say it's guided, because it has what we call a heuristic function. So this is what we call a heuristic function. The heuristic function itself is just this part here. It is a function that maps the Cartesian product of the vertex times itself to non-negative real numbers. In other words, between any two vertices, give me an estimate of what is the length of the shortest path between those two vertices. It only has to be an estimate, and the estimate, in order to be usable in the A star algorithm, it has to be admissible. Admissible simply means it is always an underestimate of what it really is. Is that okay? So let me sum it up. Okay, the function h is basically estimating the shortest path, the length of the shortest path between two vertices, and it only has to be an underestimate. Or let me correct that. It cannot be an overestimate. It can be exact, but it cannot be an overestimate. So that means if you just map every pair of vertices to 0, that is legitimate as a heuristic. It doesn't buy you anything in that case, but it is still a legitimate heuristic because it is an underestimate, and it is also a non-negative value. Is that okay? But what is the context? Why do we want to have a heuristic? To explain that, we'll go to San Francisco again. So we go to San Francisco downtown, and then we go to Google Maps. Okay. There we go. All right, so let's zoom in one level, 2 levels. There we go. So let's just say that we are going from we are trying to find the shortest path, this time from one location to another location. So let's say we are trying to go from, we're trying to go from the BART station, from Embarcadero to Dragon's Gate, okay? So I'm trying to find the shortest path between here. No, that's too easy. Let's find something that's harder, okay? Something that's not as straight of a line. Okay, Trans-America Pyramid to San Francisco Museum of Modern Art, okay? That's not so straightforward, okay? Dijkstra's algorithm would look at the destination, and then it will just zoom out. It would just kind of expand Q. So if Q is representing the boundary of what it's exploring, the boundary is just kind of like radiating. So it would go to a lot of destinations, or it would go to a lot of sources, like Museum of Ice Cream. That is not really what I'm interested in. we can stop as soon as we get to Trans-America Pyramid, but it will basically end up exploring more or less a big circle like that. Is that okay? And that's what Dijkstra's algorithm would do, because Dijkstra's algorithm starts from the destination and it expands out from destinations to cover all the vertices. Is that okay? So it's not guided, and by the time we find the shortest path, we would, from Trans-America Pyramid to San Francisco Museum of Modern Art, we would have found the shortest path of many, many other vertices to San Francisco Museum of Modern Art, which is not what I'm interested in. Is that okay? So yes, it works, okay? And it works really well if you're interested in the shortest path from every vertex to a destination. But it's not very optimal if you just want to find a shortest path from one single vertex to the destination. Is that okay? So now we try to look at things from the perspective of A-star algorithm, or anything that makes use of a heuristic. So the heuristic is easy in this case. The heuristic between any 2 points is really just the straight distance between those 2 points. Okay? So you look at, from Trans-America Pyramid to San Francisco Museum of Modern Art, and you just go like, we'll just measure the air distance, or line of sight distance between these 2 points, and we'll use it as a heuristic. It's just an estimate of what is the actual distance between those 2 points. Is it guaranteed to be an underestimate? Yes, it is. Okay? Is it always going to be non-negative? Yes, it is. So now it becomes a useful heuristic, because we're also going to use the same heuristic from any point from this entire graph to the destination of San Francisco Museum of Modern Art. How is that going to help us? Well, with the A-star algorithm, we start from the source. We don't start from the destination, we start from the source. So starting from the source of Trans-America Pyramid, it will look at all the connected vertices, and then it will ask, well, which one looks like it is on the shortest path? Well, how do you know it's on the shortest path or not? Well, I mean, let me point out here. So how do we know it's not a very bright idea to consider Washington Square to be on the shortest path to San Francisco Museum of Modern Art? How do we know that? Because the heuristic from Washington Square to San Francisco Museum of Modern Art is longer than, let's say, the heuristic from even Embarcadero to San Francisco Museum of Modern Art when we are starting from Trans-America Pyramid. Is that making any sense?
How are you going to know that? But how are you going to know that?
How are you going to know what?
Like that, the distance between Washington Square and...
Because we are only looking at the air distance. So we're only looking at the straight line distance between the vertices. So we are basically really literally measuring this to here, that straight line, as opposed to this straight line here. Okay? So that becomes a useful guiding, mechanism, because now we can look at all the outgoing neighbors of Trans-America Pyramid, and then for each of the outgoing neighbor, we then evaluate what is the length from Trans-America Pyramid to that particular vertex, plus what is the estimate from that vertex to where we want to go. So that sum becomes a realistic estimate. So when we go backwards, then the sum of those two distances is going to be longer than when we go forward like this. So that means, when you look at the A-star algorithm and what vertices it will try to explore, it's going to explore things that are kind of like between it will explore, it's a more directional exploration. As opposed to a breadth first search, this one is directional. It's guided by the heuristic. Yep.
So you're saying as it goes on, it's going to take those new distances to the destination and add it to the distance you'd be traveling from where
Right.
Do you need that distance from where you're leaving?
Yep.
Can't you just like look at all which ones?
You have to look at the sum.
Can't you just look at which one's the closest and then just go on that path then and look at which new vertex is closest and then go to that one?
Well, you still need to keep track of, how long or what is the distance from the origin to the vertex that you're looking at. So that one is tracked precisely, so what is the actual distance from your origin to a particular point. But you have to add the estimated distance from that point to your actual destination. So that sum becomes a number that you can use to see which vertex you should look at next, which one looks the most promising. Then you just you explore in that direction. Okay, so are we okay so far with the vague conceptual at a very conceptual level? What makes the A-star algorithm different from the Dijkstra's algorithm? It is the use of the heuristic function. Okay, that is really the key. Okay, so let's go back to the notes. I'm going to turn this off and go back to, nope, not that, to the A-star algorithm here. So in order to use the A-star algorithm, we'll need basically a few ingredients. So we'll need the heuristic function, and typically the heuristic function is something that is easy to compute, like the distance of a straight line between 2 points in 3 dimensions. That's pretty easy to compute. So the heuristic is just a rule of thumb, easy to compute, guaranteed not to overestimate kind of function. Okay, so as long as it meets all those requirements, it can be used. And then this is, this L here is representing kind of the same notation as before. It is the length of the shortest path between 2 vertices, but this time it has 2 parameters, because we have to indicate from which vertex to which vertex. Okay, this is the actual shortest path. And what we want is this statement here. So for every pair of vertices, we want to make sure that the heuristic going from V to W is always less than or equal to the actual length of the shortest path from vertex V to vertex W. That is a requirement that we need to place on the heuristic in order for A-star to work. So we'll go ahead and talk about the algorithm now. The graph is still, VE, okay? So the same assumption as before. We still have a distance function. That is just looking at a single edge and ask how much does this edge cost, okay? So D has the same meaning as before, which is really just the number on top of an edge. That is the cost of an edge itself. In this case, we need to define what is the start vertex. And this is also a difference between A-star versus Dijkstra's algorithm. In A-star algorithm, you have to designate where are we starting from. Okay, so that is a requirement. We'll also designate which one is the destination. So you need a start vertex. You also need an end or destination vertex in order for A-star algorithm to work. We talked about the heuristic function already. So we need all of these ingredients in order to start the initialization. So this is the initialization. The initialization has to initialize 2 functions. One is called G and one is called F. So we'll take a look at this for loop here. So for every single vertex of V, we have to do the following. The first thing we need to do is to ask, are we talking about the origin or the source of the whole thing? If not, then we use these 2 equations here. Or not equation, but we use these 2 assignment statements. So these 2 assignment statements, G is denoting the actual length of the shortest path from S to V. And then f, on the other hand, is the estimated length of the shortest path from S through V to X. Okay, so do we see the difference? I'm going to draw a picture to show this. Okay. Okay, so here's the picture. So G of V is representing, this is a known actual explored path. We know edge by edge how we can go from vertex S, which is our origin, to vertex V, which is the vertex that is in question at this point. Okay, so this is a hard number based on edges and the summation of the cost of all the edges along this path. Is that okay? That's G. F, on the other hand, is the summation between G of V and the heuristic of going from V to X. So that means F of V is really just G of V plus the heuristic of going from V to X. Is that okay? One is just saying, well, I know how, what is the length of the shortest path from the origin, which is where we are at this point, to a particular vertex on the map. I don't really know exactly where that is, but we know the distance, okay, or the length of that shortest path. That's G of V. On the other hand, F of V is even more useful because F of V is an estimate. And say, if we go from the origin S through vertex V, which is the vertex that I'm looking at right now, to the destination X, what is the estimate of that particular path? So that's why it is incorporating the heuristic function h of Vx, because that is just an estimate of the shortest path, of the length of the shortest path from V to X. Is that okay? Does everybody understand what G is representing and what F is representing? Okay. So now let's go back to the initialization. Why do I initialize both of these to infinity when V and S are different? In other words, when we're dealing with a vertex that is not the origin, okay, it's some vertex on the map but it's not the origin, I'm just going to say the shortest path from the origin to this particular vertex is infinity. Well, that's because I haven't explored anything yet. There may not be an edge connecting, there may not be a path connecting the source or the origin to this particular vertex V. Of course, I'm going to make the assumption that it is infinity. Same thing applies to V, because if G of V is infinity, G of V is automatically infinity, because G of V is really, F of V is G of V plus the heuristic of V to the destination X. So if G of V is infinity, F of V is guaranteed infinity as well. That's just for initialization before we explore anything. What if we are looking at the origin? What if V itself is the origin? Well, that's easy, because what is the length of the shortest path from the origin to itself? 0. Okay, well, that's why we got a 0 here. What about the origin going through the origin to the destination? What is the estimate of the length of that path? Well, that's what the heuristic is for, right? So that's why F of V, or F of S I should say, because this is the else case, that's why F of S is the heuristic function of S to X. S being the origin, where we start from, X is the destination where we want to go. Is that okay? Is the initialization making sense? Okay, all right. And then we have another function. Previously, we used E prime to keep track of the solution graph, In this case, it's a little bit different. We keep track of a previous vertex. So prev v is really just saying, okay, in the solution graph, what is previous to vertex v? That's all it's asking. Okay. It is another way to keep track of E prime, just a little bit different. So we initialize every single vertex, quote unquote, previous to be undefined. We don't know who is before that vertex in the solution graph. So in this case, we keep track of a set called O, and it is initialized as a set with just the origin itself. So that's where we start. And then the loop is right here. This is the for loop that we have to follow through when we execute that algorithm. So let's go back to the graph that we had earlier, okay, that we already used the Dijkstra's algorithm on, and then we'll try to apply the A star algorithm on exactly the same thing. Okay. So we go back to that graph. Okay. And then we'll copy and paste this to a new place. It won't cross a page. That's just for layers. Let me try that one more time. We can use that tool. I don't know how to copy and paste. Okay, this is copy. And maybe this will work. Nope. Oh, I just need enough area. We'll just put it here. But we can't do it until we have all the heuristics. So we'll have to define all the heuristic values. And so we'll define BE, the heuristic value of BE. It only has to be an underestimate. We can easily make it 0. But instead of 0, we can also make it so that it is just some kind of underestimate. 2 would work. And then we have CE. So you look at CE, it's actually 3, so we can make this even 2.5. In other words, we do not have a monotonic heuristic. It will still work. We have DE. DE is the distance is exactly 2. We can underestimate that too. So we can underestimate that to be a 1. EE doesn't make any sense. And then we have AE left. So AE is 3.1, and we can make this 3. So now we have just some randomly assigned heuristic value. The only requirement is they cannot be overestimates. And none of these is overestimating. And some of these actually has some not so nice properties of being non-monotonic. Okay. So now we can go ahead and try to track our, algorithm. Just want to put this at a place where it is a little bit more compact, because I will need to display both the graph and the trace at the same time. So here's the graph, and then we'll take a look at the trace here. So this time we have a set called O to begin to track, and then we'll look into the algorithm itself, because I need to predetermine how many columns we need. We need F and G. That's going to be a little bit complicated. We have to choose a vertex C from O to work from. So vertex C is kind of the same thing as a vertex V in the previous algorithm. It's just whatever we are choosing to explore this time. We also have a neighbor, so we have 2 more variables to track. And then on top, we have a whole bunch of G's and V's that we have to track. So we have to choose a C, and then we have to choose an outgoing neighbor, this time N. And then we can look at all the G's as 1, all the F's as 1, and all the previous as 1. Okay, so this it's going to look pretty ugly. Okay, so we have to look at all the G's. So we say G of, okay, let me show the graph again. So in the initialization, everything other than the origin is going to have a G value of infinity. So G of B is the only one that has a value of 0. Everything else is going to be infinity. So G of A is infinity. G of C is infinity. G of D is infinity. And then G of E is also infinity. And we'll choose to wrap around here. Here we go. F is kind of the same thing, except F of B is just the heuristic of going from B to E, which according to the way that we define the heuristic function is 2. But everything else is going to be infinity. So this is 2. F of A is infinity. F of C is infinity. F of D is infinity. And then F of E is also infinity. So once again, we'll format and use text wrapping. And then all the previous are unknown at this point. So can we just say that they're all unknown? All unknown. Okay, that makes it easier to say. Okay. And O is initialized to be just the start vertex itself. In this case, it is vertex B. And that's our start condition. Are we good? Are we doing okay so far? Okay. Now that we are done with the initialization, the first thing we pick is the most promising vertex within the set O. Most promising, so let's go check out what is most promising. I know we only got one vertex and we don't really have to choose, but we want to read it anyway. So now we are basically taking a look at this sentence here, and how do we define most promising this time? So most promising this time is based on the function f. In other words, we are looking at all the vertices in O, and then we say which one seems to have the shortest path to the destination. That becomes the next thing we want to explore. Is that okay? Now, how is this different from Dijkstra's algorithm of how we choose the next vertex to explore in Dijkstra's algorithm? In Dijkstra's algorithm, we are choosing based on the length of the shortest path from a vertex to a destination. That is already known. It is already explored. There are actual paths that exist already. In this case, it is not, because one component of f is based on the heuristic. So these are all estimates. We are basically looking at the estimates and ask the question, according to these estimates, which one looks the most promising? So now, if your heuristic is very accurate, then this becomes very guided. Every single time you pick, you are picking the right one. On the other hand, if your heuristic is not informed, okay, it is just 0, you're mapping all the h values to 0, then it's not informed. You're just picking more or less blindly. It becomes basically the same thing as breadth first search. So getting back to our algorithm, okay, this time it's easy because we only got one element, has got to be that one. So we choose B, and now we look at what are the outgoing vertices from B. So when you look at the graph, B has 2 outgoing vertices. It has got A and it's got C. Okay, we'll pick A first. The order doesn't really matter. So now we pick A as the first outgoing vertex to explore. And we look into the algorithm and go like, okay, so what do we do? Well, the first thing we do is we remove it from the set O so that we don't, have an infinite loop. Okay, that's easy enough. So the set O is now, oops, there. Okay, so that has to be done in the previous step. But what do we do with A? A is our outgoing neighbor. So the first thing we do with that outgoing neighbor is to compute this value here. We are computing the shortest path from the origin to vertex C, and then we are adding the cost of the edge from C to N. Okay? So what does that translate in our case? So what we are looking at is, what is G of C? Or G of vertex B in this case. G of vertex B is 0 because that is our origin. Okay. If I go from vertex B to vertex A, it has a cost of 0.5. So that means the shortest path from the origin to vertex A is 0.5, or one path has a cost of 0.5. Is that okay? So the next question is, okay, so we'll remember that. And then back to the algorithm. Then the next question is, did we find a shorter path? Did we find a shorter path from the origin to vertex N? That's the next question. So what do you think is the answer in this case? So getting back to the trace again. According to this column, okay, according to this, what is the length of the shortest path from the origin to vertex A? It's infinity, okay? Because we have never seen any edges before from reaching vertex A. But 0 plus 0.5 is 0.5. 0.5 is less than infinity. So the condition is now true, so we have to go into the conditional statement. What do we do in the conditional statement? Quite a few things, kind of the same thing that we usually do in the other one. We have to add the outgoing neighbor to the set O because we are going to change something related to that neighbor. So we'll go ahead and do that. So O is now including A. But we also have to change these things in G and F, and also previous. So let me just go ahead and make all 3 wrap around because that's what we need to do. So we'll wrap text in all 3. All right. So with G is the easier because the value of T, we just need to update A with that value. So G of A is not infinity anymore. it is now 0.5. Because we now know the shortest path from the origin to vertex A has a cost of 0.5 units. But that means we also have to update the f values. Okay. But how do we update that? The f value is the g value plus the heuristic from vertex A in this case to vertex E. So we need to show the heuristic values in order to calculate that. The heuristic value from A to E, according to this, is 3. 3 plus 0.5 is 3.5. So that means f of A is, instead of infinity, it is now 3.5. Is that okay? And then we also have to remember, according to this shorter path, the previous of A is B. Okay? Vertex A has, vertex B has another outgoing neighbor. Vertex B go to A, but it also goes to C. So now we have to say, well, let's consider C also. And the first question is, did we just find a shorter path from the origin, which is B, to vertex C? The answer is yes, we did. Yes, we did, because at this point, before this exploration, the length of the shortest path from the origin to vertex C is infinity because we haven't explored a single thing yet. But now we say, oh, it is just 1. So 1 is less than infinity, so we have to update that value. So we go into the conditional statement, which has several things to do. This is now A and C, and then the G values. Okay. Now has G of C updated to 1. But then the f value needs to be updated as well. The f value is, oops, there we go, click, there we go. So the f value is based on the g value plus the heuristic. The g value is 1, and then the f value from C to E is 2.5. 1 plus 2.5 is 3.5. So we update f of C from infinity to 3.5. But then we also have to remember the previous of C is also B. Is that okay? So we are basically step by step, just exploring out in this case. Do we have any more outgoing neighbors from C? Nope, we're done, right? From B, sorry. So from B, we have A and C as outgoing neighbors. So now we have explored both of them. So that concludes the for each inner loop. Then we go back out to the outer loop. The outer loop looks at O and go like, is O an empty set? No, it's not an empty set. It also looks at, are we at a destination? Nope, none of the vertices in O is the destination. So now we have to pick one of these two to expand, but it's based on the f value. So you look at the f value of A, it is 3.5. You look at the f value of C, it is also 3.5. In other words, it doesn't really matter in this case because it's a tie. So we'll take a look at C first. Okay. So we'll say, well, let's take C out so that the set only has A left. And then we have to look at, okay, what are the outgoing edges of C? The outgoing edge of C, there's only one, it goes to D. So now we look at D, we look at the edge CD, and then we look at, well, have we found a shorter path to go from the source or the origin, which is B, to vertex D in this case, through the edge CD? Well, when you look at these values, g of d is infinity, which means we haven't found a way, a single path to go to vertex d at this point. We have just found the first path, so it has to be the shorter path. Okay, so let's go ahead and update that. So we copy and paste it over here, and then we look at g of d, and then we ask, well, how are we going to update this? This value has to reflect the g value of c plus the cost of the edge of CD. G of c is 1, and then the edge of CD is also 1. 1 plus 1 is 2, so the new g value of d is 2. But then we also have to update the f value, because we now know the shortest path, the length of the shortest path up to this point from the source or the origin to vertex D has a length of 2. But what about from E to E? Well, you can say that, well, it's only 2, but we don't know yet because we have not explored that edge. So all we can rely on at this point is the heuristic. The heuristic is going to say, well, it's an underestimate, it is 1. So we add 2 to 1. That makes f of d 1 in this case. Excuse me, it will be 3. 2 plus 1 is 3. So we go here, and then we update this value to be 3. And then we also have to remember the previous of d is c, on top of everything that we already know. So Control C, and then Control V, and then we add that new piece of information here. The previous of D is C. Do we have any other outgoing neighbors from vertex C? Nope, that's it. But we also have to add D onto this set here, because every time we change a value of a particular vertex, it has to be added to the set O. So what do we do with O now? We have 2 vertices. I know we are running out of time, so we'll continue from this point on Wednesday. But the key now is we look at the F values. D is actually more promising. So we're going to expand D next, because it has a heuristic value of 3 as opposed to the heuristic value, or the estimated shortest path from A is actually 3.5. Through A, sorry. The length of the shortest path through A is 3.5. The length of the shortest path through D is 3. So we'll continue from this point on next time on Wednesday.